Okay, this is session 23A, first part, and we are going to continue with a description of the support and of a spectrum of a measure, respectively of a mild distribution. I have done this to some extent last week already, but I will try to do some corrections, or actually corrections. So the first thing is, let's recall how to say a set of area is trivial, a point is having trivial action. Well, if you find a function which is takes the value 1 or some non-zero value at the given point, and you multiply your distribution with k, which means you're looking at the action of sigma on all the localized versions of your f functions. And if this can happen, then if this is 0 for all possible input signals, then it's said to be a set of trivial action. So roughly speaking, you localize your sigma, and that's possible due to this multiplication. And there it's the 0 functional in this area. So it's not meaningful to take pointwise values, but it's meaningful to say something is 0 or something is equal to something else if you localize it by pointwise multiplication. Now, I don't go into this once more, but it essentially, there was only a correction. If you're testing it on all the functions which are living in that area, and if you're saying all those which have local support are put to 0, then you have an equivalent condition. And it's easy to do it for measures, but also for distributions. And maybe I should mention something that I've added here. You can either test only on if you have a measure, you're allowed to test on any continuous function. If you have a mild distribution, you have to take them from the Fourier algebra as well. Now, you could take an ordinary bounded measure and test it only on these elements, but that's the same as testing on the continuous functions, because we can approximate an arbitrary continuous function by a measure, by function in the Fourier algebra. So that's really, it does not depend on the algebra that you choose. It's good that you have small functions with small support, as we know, take the triangular function, and that we even have this Fourier inversion theorem. I try to avoid it, but in most cases, it's not a problem. We also have mentioned, and it's easy to verify it, I have described now a little bit better, that the classical support, which is the closure of the set of points where the function value is non-zero, is consistent. That means this classical definition gives you some closed set. By definition, the bar is the closure. But if you take a distribution induced by the k, so what we call mu sub k, which is also a sigma sub k, then it also has a support now in the new definition, namely the complement of the set of trivial points. So I would say, what is a point in the support? It's a relevant point. For a function, relevant points are those with non-zero. For a distribution, you cannot do it pointwise, so it's important to think of opposite of trivial action, and therefore you have an open set, and the complement of an open set has to be closed. So there's only a chance for consistency if you have the closure here. So I would motivate this here. Also indicated that for Lebesgue integrable functions, this concept is not meaningful because you're allowed to change a function pointwise at countably many values, and that would not affect the thing. Another notion which is now quite easy is the notion of the spectrum of a support of a mild distribution. You just give me a element sigma in S0 prime. I can take the Fourier transform in this simple way. Sigma hat of f is f, or sigma of f hat, as we know all the time, and it has a support. Now, the classical thing was a very general, a very indirect definition for L infinity functions. Now, L infinity functions are either, if you want to see it in this way, are either functions which are measurable and essentially bounded, or they are elements of the dual space. Now, for us, maybe that characterization would be more natural. We could say, well, you start with S0 and you take the closure of S0 in the L1 norm. So Riemann integral allows you to take the L1 norm. We define L1 in the same way as we did it with L2. So clearly S0 or many other ways, S0 is dense in L1. Yeah, for example, we have also seen that any band-limited function in L1 actually belongs to S0, and they are dense in L1. So okay, because you have a dense embedding of S0 into S0 prime, if you take the dual spaces L infinity, you call it L infinity even if you don't know much about it, the dual of L1 will be inside S0 prime. So of course, elements of the dual of L1 or these essentially bounded measurable functions, they have a Fourier transform in our new sense, and that has a support. And there is a definition going back to the book of Hans Reiter and of course earlier, where it was said that you can do it, define a spectrum, and this classical definition and the natural one in the distributional context are the same. Of course, I should mention, if you're familiar with tempered distributions or you learn about them, you also define a support of a tempered distribution, and you test only against a smaller subspace of S0, which are the Schwarz rapidly decreasing functions. But for this space, you get the same support. So whenever a support is defined by application to localized test functions, if they are rich enough, everything is fine. Okay, and then one of the main theorems was the support characterization. We have weak star approximation of a point in the support. So T is an essential point for your distribution. If you can localize it, or you can find a family of functions K, which are kind of more and more narrow, concentrated near T, and suitably chosen, such that when you act on a finite set of test functions, you have a given approximation error. Of course, I don't go through the proof once more, but I was saying we can reduce everything. Now I have introduced the letter G here. So for all these finitely many functions, they have inverse Fourier transforms. And they are in L1, and therefore they are concentrated in some domain. So most of the functions or L1 norm is sitting inside a plateau function. So for each of those finitely many functions G, we can multiply them with a plateau function of finite size, and that difference will be small. So we fix such a plateau function. Now then we start with another trapezoidal function, and we want to compress it in a certain way that requires us to take a parameter rho, and that parameter rho should be chosen such that the concentration of the tau is so strong that the kind of shift invariance of the Fourier transform of this, and you see there is a V divided by rho, is small. Now we need this for all the points V which are in the support of our plateau function P. So once we have fixed the P, we know that this V will not be larger than capital R. If we divide that by rho, and rho is very big, then the whole difference will be small. T tau's hat is a function in L1. So this will be a very little shift for this function tau hat. And now there was one mistake, and that's kind of this orange correction or so. I forgot to tell, I mean, I was using part of this on the Fourier transform side, but I forgot to say what we know is that sigma multiplied with a sequence Kn can always be chosen to be non-zero, even if you require me to choose the support of Kn to be very, very small. Now, there is some parameter rho that has been chosen beforehand, and it's fixed. So I can compress my function tau in such a way that with a dilation, so the dilated version of tau, this one here, can be made such that the plateau is still reproducing the little k because the k has such a tiny support. You can imagine that really means that that the k rescaled is a Dirac measure, maybe even a rescaled Dirac measure. Now, if you choose your tiny plateau function, which has a very flat Fourier transform, such that it reproduces the k. So rho is chosen, tau is chosen, this is fixed. We choose within the possible choices of our red condition some k which is just very narrowly concentrated. Then of course sigma times k multiplied with d rho t, as you can imagine, it's just inserting this is the same as sigma times k d rho t, but you can pull that out. So we have this nice reproducing property. But now, and that's the freedom of distribution theory now, you can say, well, this is a pointwise relationship. We go to the Fourier domain. So this Fourier transform of our localized distribution is sigma k hat. And then instead of dilation with a parameter rho, and you think it's getting more and more narrow, we make a wide stretching. And if you stretch to the amplitude by 100, no, the basis is stretched to 100 times the size, then of course, because this is norm preserving in the L1 sense, this is a very flat and low function with small values, but it doesn't matter. We have already stored the good invariance properties here. And now the trick comes here. We know that sigma times k is not 0. We also know that it is reproduced by some function which is in S0. So we can say it's a functional called sigma k hat, convolved with some nice test function. And we know how to do such a convolution. It's an abstract convolution, but it can be made concrete. Take this distribution, applying to that function in a flipped version, shift it to some point. So clearly you get a continuous bounded, even uniformly continuous bounded function. Okay, so we know now this is a nice continuous function. And it's very plausible. It's very well concentrated. Also, it could be a delta, a distribution, or something like this. Now, if you give me any bounded function, it will take a value near its maximum, maybe larger than 1/2 of the maximal value. And therefore, if you're saying, well, pick such a value where it's near the maximum, or not the maximum, the supremum, it could be asymptotically, we don't care about this. So if I take such a value where it's almost near the sup of these functions, then of course, by rescaling the function sigma k by that number, in the footnote you find the details, then the overall function Fourier transform is at most sup norm equals to infinity, sup norm at most 2. And so you have a function, maybe the maximal value is 1/100, and you choose a value which is 1/120 or so, a little bit smaller. You rescale by 100 or 120, and you get a function which is a little bit bigger than 1, and you can control it, that this rescaling doesn't blow up the effect by choosing the function S. Now, what does it mean if the S0 is not the midpoint, the 0 point? We have to modulate our k, and then we have a shift on the Fourier transform side. So we can assume that this is 1. That's just again for simplicity. Now the rest of the proof is exactly as we have discussed it already, and I don't want to do it once more. Essentially, I call this function a sigma k hat h. And we know from this invariance property that h is very big on the support of our plateau function p. So when you multiply your inverse Fourier transform with the p, it's an easy estimate. You have the sigma 1 is constant 1 integrated against gp. So this is this with the p, minus the sigma h means this written out. Now, for all the values which are relevant here, you only need to take the ball of radius r. On the rest, it's 0. But on the rest, on this is a small thing. It's very close. The h is close to 1. And therefore, you have this epsilon 1/2, and then you put things together, and you're done. So this was essentially the main step. And to come back, what it tells us is that the action of sigma of constant 1 against the inverse Fourier transform Rf is the same as the action of Rh on the G. Now, looking at the formula for inverse Fourier transform, we realize what we have shown by taking inverse Fourier transform. Again, it's a lot of flexibility here. You get inverse Fourier transform of constant 1 is just the delta. The forward Fourier transform of the G is the f, because G was the inverse Fourier transform of f, so we just go back. Minus, and the h was the Fourier transform of sigma times k, so we're going back again. And then we have the FA. So if you rewrite it, you have exactly the expression that we need, and everything is fine. Now, if you take the same result and want to characterize as a spectrum, then you are just having weak star limits, and then instead of the functions k and which are multiplied, you're doing a convolution, because then you would get the gn hat multiplied with sigma hat, and sigma hat, the support of sigma hat is the spectrum of the original distribution. So it's just a translation of this earlier result into these things. Here I wrote down that the spectrum defined in an indirect way in the book of Reiter is the same as this. And there are several properties. For example, if you multiply a distribution with a test function, then the support of the product is of course contained in the intersection of the support. So multiplication makes the support smaller. And that's like functions. If you're having two functions, we know the pointwise product is 0 whenever one of the constituents is 0. And therefore, the product function has a support which is contained in both of the supports of the individual factors. Such a thing is easy. And I also mentioned that if you split a distribution with BUPU, and we know that we can do it, this is meaningful. The sum over all the sigma psi i's are weak star convergent to sigma, simply because if you test it against a compactly supported test function, once you have the finitely many relevant elements psi I, which are covering the test function, you're done. So this is quite easy to solve this. Now, I have mentioned now a result which is a little, or introduced a new statement in the text, which is a little bit more general than the one we have, or than the idea that we had. So the first statement is, if you're giving me a distribution, a multi-distribution in the test functions, and if their supports are disjoint, so now there's no common point, then sigma acts trivial on f. So somehow, if the f is living completely in the region where you have trivial action for all those points, then of course you decompose your f into pieces and the action is trivial. So the formal argument is the following one. It's enough to do this for finitely supported measures, because every f is the limit of the partial sums, so the finite partial sums of the pieces. So you can imagine it's a limit in the S0 norm, so if you have this for compactly supported functions, it's fine. Now, maybe you have a more elegant argument, but I was using the following argument. Call M the support of your distribution sigma. So this is M. We can assume this is a compact set, and then the distance of two compact sets is, the distance of a compact set to a closed set is a positive number. I use this compactness argument because it's not true that the distance between two closed subsets has to be positive. It doesn't have to have a positive distance. Just take the graph of the exponential function. Maybe you take the graph of e to the minus x. So it's a curve, and clearly that curve is touching tangentially the x-axis. So the graph of the exponential function e to the minus x is a closed curve in the plane. The x-axis is a closed point in the plane, but there is no positive distance, because if you go very far or just far enough to the right, you have arbitrary small distances. But if you stop somewhere, so that's the kind of the trick, if it's compact, then there's a positive distance. So I'm taking the set m, I'm taking these finitely many functions psi I, they are living somewhere, they are all together living in a compact set, and therefore this distance has to be a positive distance. And now we are splitting our sigma, the index set for our very fine BUPU, into two parts. And it turns out that either you are near the support, and then you can use certain elements from your family, or you're kind of near the support of F. So there's enough distance to do it, so that when you're saying, well, what is the total action of sigma? Then you're saying, well, either my localizer psi I is in the first index set, where sigma with psi I is 0, or it's in the second set, where the function f is 0. And therefore, you are adding up two parts. Altogether, these two indices are together giving the whole index set, so you are having 0. So that's relatively easy. I'm not sure if I can find, yeah. Here there's a remark. If you have two ordinary functions and your distribution is coming from a bounded continuous function h, then of course, and the action is the usual one, integrate your test function f against h of x dx. Then of course it's enough to know that the support of h, which as we know is the same as the support of the distribution sigma h, intersected with the support of f is 0, or even sorry. Yeah, kind of not, you don't need this, you need something less. You need that the product function is 0 in order to guarantee that this integral will be 0. And that of course can happen, that you may have functions, for example, this h may be a triangular function living on -1, +1, and then you shift it, and you have a triangular function living from +1 to +3. Then the supports are not disjoints, they're touching at the midpoint, but still the product function is 0. So it's not completely clear that you can just say what I claim here, that if you have a function and the function has kind of an ordinary set of relevant points, this is of course a typo, you take all the points x such that f of x, oh, that's double typo, x such that f of x is non-equal to 0. So you're taking the relevant points, and if there is no, I mean, to say if f is 0, it should be either you can say it should be a containment. If the support of mu is inside the points where the function is 0, or you're saying that the intersection with the complement of this is empty, that would be the same. But maybe we say if the support is inside the set of points of measure 0, then you have 0 action. And it sounds so natural that you're wondering why you need a proof, but the proof is has to be given, and I would like to give you an intuition more than a too abstract proof. So I took a cosine function, as you can see, on 0 pi. This function has clearly at 0 at pi over 2, and what I suggest is the following. We can modify this function, which has this isolated 0, by making it flat, and by flattening it out, we can make a very small error, and this is more or less the functional analytic trick that we use in this case. But it only works, not, you see here, it's not a mild distribution, but it's a bounded measure. Okay, so how can we do it? I mean, I actually did this with, of course, with MATLAB again, and I was creating a very fine poo-poo, and I was saying, well, this function is, of course, the sum of all the small pieces. But if I leave out, let's say, 2 or 3 of them in the middle, I think I was taking 3 of them, very narrow ones, you get a 0 in some small domain because I had adjacent elements from my poo-poo. But what is the correction or the change I introduce? What is the epsilon error? So kind of you could draw the original curve and epsilon strip or so. Of course, that will be very small if your plateau is very small. And this has to do with the difference. So here, look at the scale. So here the function is scaled from -1 to +1. And I just plot here the difference, and the difference that has been subtracted is, of course, positive on the left of pi/2 and negative on the right. And it has a small amplitude. If you're willing or if you're requiring a better approximation, you make this flat area a little bit smaller. And then, of course, also the amplitudes will be decreasing. Now, the trick essentially is described in a formal way, again by the following argument. I just give you an indication. You don't have to learn it or so. You just should see that this can be done in a mathematically precise way. So we are looking at a function which has zeros. So the zero set, sometimes also written as f to the -1 of 0, but it's the point set where this function has zeros. And we want to do an approximation by something which is not 0 only here, by something in the delta neighborhood of this set. So you're giving me, you're giving me an epsilon, and I find by the continuity or uniform continuity some delta such that this difference for y less than delta, actually we will do it for 3 delta, so we choose the delta that you take usually and replace it by 3 delta, such that you can guarantee that for every x, wherever you are, you have this estimator. So now with this 3 delta, or the delta that we get from the uniform continuity, we get a poo-poo of that size. So it should be a delta poo-poo, so kind of 3 times as small as required for this condition here. And then also we take this, we can squeeze a triangular partition of unity in 1 dimension, for example. Of course, we can assume that these psi's are non-negative. Therefore, whenever we need it, we can write absolute value of psi I is psi I. And now comes the trick. We do a kind of splitting again, the ones which are near the 0 and far away from the 0. So in the case of multidimension, that's kind of not completely trivial. You have a lot of lattice points. The 0 set of a continuous function can be a quite general curve, but all those points, it can be many, many points or so, that are not further away. I mean, each of these supports are compacts. They're sitting inside a ball. So the distance is really taking a minimum, but I'm taking only those indices which are having the support already a little bit at a distance. Well, I'm taking all the ones which are near this zero set. So kind of the ones which are not taken having at least a distance to this 0 set of size delta. That's the trick, so to say. Okay, now if you give me any such element which is in this index set, which is the kind of the index set attached to the set of zeros of our function, then of course every point in the support of such a psi I has to be, because of this assumption we have a delta poo-poo, has to be in a delta ball around its center, xi. So what can you say about the distance of such a point? So if you have kind of the question is, we have to use certain functions psi I, and where are they? And I'm just saying they're not far away from this set of points of set of 0. Okay, and the distance is, of course, well, you go from the center to some point in the 0 set, and the 0 set And on the other hand, you go from the center to x. So maybe I should write it in a different order. Maybe distance from z to xi plus the difference from the center to your point. And then you get 1 delta plus 1 delta is 2 delta. Okay, so somehow all the non-trivial values of our functions psi I are at maximal distance of 2 delta from a point where your function is 0. Okay, now we're writing the sum over all these unimportant contributions which are near the area where f is small. Okay, so it's the absolute value of a partial sum. I mean, locally this is a finite sum, so this is harmless. And actually, this is how I was implementing it in MATLAB. That's really also true. I was searching for those indices where my psi I is near the 0, and then I was adding up this partial sum. Okay, so this absolute value of a sum is at most pointwise finite sum. It's just triangle inequality, the sum of the absolute values. But what you know is that now the x is not far from a point in the 0 set. So f of x is actually f of z. Maybe I should spell that out a little bit. From the 0 set plus an error which is at most 2 delta. And this change of the delta means, maybe I also should write z plus y or so. Means that now this function value, this difference from a value of 0 will be at most epsilon. So deviating from a point, being not far away from a point where f is 0 means the f has to be small, which was of course the original idea. But if you pull it out, this universal estimate, the remaining thing is the sum of the psi I, and we have seen they are non-negative, therefore they add up to 1, so that's epsilon. So all these guys are small. And now more or less the same trick comes that we have seen last time already. You split your function f into 2 pieces, f plus f1 plus f2, with f2 being just the difference, and that's of course the remaining things. These are the things where are far away from the set of measure 0. But by the assumption about our measure, we can do the same trick now. We can say now m is a linear function also. M applied to your function f, which has some zeros or so, will be the small part plus the irrelevant part. Now, what is the irrelevant part? This is the different, this is the small guy that I have shown you that they have displayed. This was, in our case, this tiny function or so. So if you act with this, you're getting a small contribution. So mu applied to f1, that's the part that you estimate here is the size of the functional. And now it's important that it's a measure. So you can estimate the size of the functional by the norm of the functional times the size of the input. And this is smaller than epsilon. But what is the f2? So the f2 is in my picture that was given first, this modified function. And if you're asking where is the support, I mean, I'm concentrating on this here. Well, it's with some distance, which is good enough so that your mu is living either here or here in our case. Okay, so this is the second part. Because it's living far away, you can apply this earlier lemma, and you get mu of f2 is 0. So this part is 0, this part is small. Okay, now you can play this game with arbitrary fine bupus. The finer your bupu is, the better the epsilon estimate will be. So mu of f can be universally estimated by an epsilon which is arbitrarily positive. Well, the only number which is smaller than any strictly positive number is of course 0, and therefore mu of f absolute value has to be 0, which means mu of f is 0, and that was the claim. And essentially the idea is this question of synthesis. Can you do the same with the Fourier algebra? And the answer is no. It's not possible all the time to do the same kind of splitting, assuming that now you would require not the infinite, the subnorm being small, but the FL1 or the zero norm, let's say. The zero norm should be small. Now, I was giving an argument, I don't have to repeat it, that, well, if the spectrum is just a one point, then you can do this trick. So this was the lemma saying that the ideal of functions in a zero which have integral zero, that this, or in, let's say we start in L1, you can do it, and then you transfer it. In L1, you take in L1 the functions which have integral zero, or you go into the Fourier algebra and you take the functions which have pointwise value. Fourier transform zero is zero. Now this is a nice closed ideal. It's a maximal ideal, and this closed ideal has approximate units. And these approximate units can be chosen. That was another plot, a blue plot last week. Can be chosen to be zero near the origin and with compact support. So it was the difference of a huge and very flat plateau, not flat, huge and wide plateau function minus a very tiny one, because we were doing something on the Fourier transform side. We know a trapezoidal function is something like a bump function. So you take an approximate unit, so you make it Dirac-like, you compress it, but then in order to have total area zero, and I was demonstrating this with GeoGebra, you would take a very, very flat version of this, because that is an approximate zero. So the trick was, you get something with integral zero, which acts only on functions with integral zero as an approximate unit, and this helps you to get this corresponding proof for a single value. So you can say that if you have, just repeat the statement, a mild distribution with support being a single point, then, okay, the first statement is, then you can say that you get a zero for any function which is zero in some neighborhood. So this is the splitting that I was already saying. But the more interesting thing was that if it's having this single point, then it's a multiple of the Dirac living at this point. And I was giving some argument or like this, but the main point was that these sets, these elements of a zero which are zero at one point, which can be zero without loss of generality, they are maximal ideals. And if you are taking the quotient algebra of FL1 divided by A0, then you get just a copy of the complex numbers, and the only linear functional that you have on such a one-dimensional space. So you would say, what is the dual space of R, and that taken as a column vector? Well, that's R as a row vector. So, or it's the same with complex numbers. So this, and you had the same trick with splitting the function into pieces, and the lemma with these bounded approximate units was helping us to get a structure which is similar to the one I have discussed now. So I don't repeat this part, but the point is we are getting a very good separation. Now, I see I have another theorem, but maybe I just do the formulation, try to do the proof then, and I have prepared some MATLAB experiments. So maybe just to discuss the statement. So whereas here the support was a single point, you can imagine if somebody is giving you a support which is a which is a finite set. So you all know or remember that if you have a finite measure, discrete measure, it's the sum of Dirac measures. Take the canonical representation with a certain number of non-zero coefficients. Then it's very easy to find out that the action is trivial everywhere except on those finitely many points, and therefore the support of such a discrete measure is exactly the set of points. In a similar way, you can take the Dirac comp on a lattice, and the support will be, of course, the lattice. You have amplitude 1 at each of the Diracs. Now, this statement is the first and important building block for doing the converse. If something is concentrated on a point, it will be a Dirac up to scaling. While if something is living on a discrete lattice, it will be a weighted Dirac comp. You can have different amplitudes. And even if it's not concentrated on a lattice, then you can talk about this if you have enough separation. So essentially, one thing is you could have a set which is, if you look at it locally, it's separated. So I don't know, you could take, I don't know, the integers, and then for every point, you add 1 over n. So you have 5 plus 1 over 5, and next to it, 5 plus 1 over 5. You have 700, you have 700 plus 1 over 700. Clearly, this would be a set which is not eta separated for any positive eta, because pairs are getting closer and closer. But the point is, it's always pairwise. So if you're near 0, or no, sorry, near 700, you would have to separate those points well enough with a sufficiently fine bupu. Maybe you cannot use one bupu for all of them, but first you localize, then for each part you still use further fine bupus. So essentially, you can go much further, but I want to show a theorem which is more useful, and the case that lambda is a lattice, and that's also why I use this letter is fine. So we are talking about discrete sets which are like this. And now the proposition which I will go to discuss after the break is the following one. For any eta that you give to me, you're saying, well, I'm interested in such mild distributions which are supported on eta separated sets, but I do not know yet which one it is, but I still can predict that if you tell me what kind of eta you have in mind, I can fabricate a constant, depending on eta only, such that you can then hand over any distribution to me which has a support on a set X, which is eta separated. And then I can already guarantee you that it is a sum of point measures. And the coefficients are uniformly bounded, and even the sup over these things can be controlled. And there's, of course, the C missing. Sorry, I see. I had it here, but I have corrected. So you can even estimate the sup over this by this functional norm of the sigma. And there's a converse, but I think I'll leave it here and I take a break now, and we should start maybe after a few minutes.